Welcome to the Deep Dive, where we streamline information overload. Today, we're rolling up our sleeves and diving into a stack of circuit diagrams that really show off the staggering potential of the humble Arduino Nano.
It's a fantastic collection to look at because these aren't just, abstract exercises. These sources show how one little microcontroller can just pivot so seamlessly.
Right.
It can power everything from, say, a fun little light show all the way up to what is essentially professional field-grade diagnostic equipment.
And that's our mission today, really, to give you the shortcut. We want to pull out the most compelling little nuggets of engineering insight from these schematics.
Yeah.
We're going to trace the electron path, so to speak, and figure out not just what these things do, but why they were built that way.
And we should probably give some context here because it's important.
Yeah, please do.
All these projects are actually being implemented by Dr. Dhananjay Gadre, together with his former student, Naman Puri. They're writing a book together called Projects Based Learning the Arduino.
Ah, okay, so this is sort of a sneak peek.
Exactly. We're getting an early look into the kinds of concepts they're developing, and that context is key, like you said. It means these builds are specifically designed to teach that intersection of code and hardware.
That makes perfect sense.
Yeah.
So let's unpack this journey. Where do we start?
Well, I think we should start with the most immediate, the most hands-on, and let's be honest, the fun applications first.
Sounds good to me.
Let's start with taking a simple physical action and turning it into a complex, visible output.
Okay, so first up is the Arduino color mixer.
Hmm.
This seems pretty intuitive. You get to be a digital color scientist,
Sure.
mixing light with 3 simple knobs. But what's the core lesson here for someone learning?
Well, the insight is really twofold. It's about analog reading and then digital translation. You've got those 3 potentiometers, they're just variable resistors, wired up to the Nano's analog input pins, A0, A1, and A2.
Okay.
So when you turn a knob, you're just changing the voltage. The Nano sees that continuous voltage, that analog input, and it converts it into a digital number. It's a perfect demonstration of analog to digital conversion.
And once it has those 3 numbers, one for red, one for green, one for blue, it has to turn them back into something that controls the light's intensity. How does the Nano take a number, like say 150, and make the light a specific brightness?
It uses something called pulse width modulation, or PWM.
Right.
Think of PWM as just a super, super rapid on-off switch. If the Nano wants the light dimmer, it keeps the switch off for a larger percentage of the time.
And for maximum brightness, it's on almost 100% of the time.
Exactly. And because this is happening thousands of times a second, your eye just blends it all together. You perceive it as a smooth, continuous dimming or brightening.
Now, here's where it gets really interesting for me, looking at the hardware. You don't just wire an LED straight to the Nano's pins, do you? The diagram shows the outputs D10, D11, and D12 running through transistors first. Why that extra step?
This is the essential lesson of signal versus power. It's something beginners often, overlook. The Nano is the intelligent brain. It sends out the low-power signal, the command, but its pins just can't deliver enough current to make a bright RGB LED really glow.
So the transistors are the muscle.
Precisely. They act as the necessary muscle, or the switch, letting the Nano's weak signal control a separate, much higher current power source for the LED. It's the difference between, say, telling someone to turn on a light and actually supplying the electricity to do it.
That's a perfect way to put it. The signal dictates, but the external circuitry does the heavy lifting.
Exactly. And moving on from there, the next fun project uses similar ideas, but it focuses more on handling a noisy physical input, and that's the dual dice project.
Rolling the bones digitally. Love it. So this uses 14 individual LEDs, 7 for each die. The visual part is pretty straightforward, but I'm curious about the input. How does the user actually roll?
The user just presses a physical switch, S1. But what really stands out here is the engineering choice to condition that signal. You see, mechanical switches, when you press them, they don't just cleanly go from off to on, they bounce.
Oh, right. They sort of flicker on and off for a millisecond before they settle.
Yes, exactly. Which would give the Nano a really confusing, messy input signal.
And you'd get multiple rolls or it would get stuck.
You've got it. So to solve this, the signal from that switch is routed through what's called a Schmitt gate, SG1. You can think of a Schmitt gate as a digital signal cleaner. It has a built-in inertia. It only changes its output state once the input has clearly crossed a boundary and stayed there.
So it guarantees the Nano gets one single, clean, unambiguous roll signal.
One clean signal. It's just clever, practical engineering.
So we've covered managing power with transistors and cleaning up messy inputs with Schmitt gates. These are really foundational circuits, the kind that build confidence. Now, if we've mastered light and dice on a desk, the next logical step has to be moving beyond that, right? Portability and more complex outputs.
That's a perfect transition. The next project, which is actually a three-in-one, the LED hourglass, Morse tutor, and POV demo, it requires all of that. Complex timekeeping, multiple functions, different kinds of input, and a really robust power solution to make it
A
mobile.
three-in-one device, that's fascinating. And it uses a 5x7 dot matrix display. That immediately signals a pretty big jump in complexity, doesn't it?
Oh, a huge jump. Instead of driving 14 separate LEDs, you're now using row and column multiplexing. You flash one row very, very quickly, then the next, creating the illusion of a steady image.
And that requires really precise timing from the Nano.
Which is absolutely essential for the persistence of vision, or POV, part of the demo.
And the inputs for this one are much more interactive. I'm seeing tilt switches here on the schematic, connected to D0 and D1.
Yeah, those tilt switches sense orientation. This is crucial for the hourglass function. It lets the device know which way is up so it can track the simulated sand falling. It's integrating physical motion into the digital world.
Plus, there's a potentiometer on D2 for setting the speed,
Yeah.
maybe for the Morse tutor.
That's it. And to give the user auditory feedback for that Morse tutor, there's a buzzer connected to D3. It really is a multisensory tool.
But I think the real learning moment in this particular diagram has to be the power system. It's so complete.
I agree. This schematic isn't just about the Nano. There's a whole dedicated power management section. It starts with a modern USB-C input for charging, but then it gets technical.
It does. I mean, if you want a professional, reliable, portable product, you can't just slap a battery onto the power pins. This circuit uses a proper charging management chip for the lithium battery.
You have to. Lithium batteries are delicate. They need very precise voltage and current control to charge safely. Otherwise, you'll kill their lifespan or, worse.
Create a fire hazard.
Right, so that chip handles all the safe charging protocols. Then you've got a simple switch to turn it on or off.
And most critically, it includes a boost converter. Why do we need that? Can't the Nano just run off the battery voltage?
Well, a lithium battery might be at 4.2 volts when it's full, but as you use it, that voltage drops a lot, maybe down to 3.0 volts or even lower. The Nano and the display, they need a stable, regulated 5 volts to work reliably.
So the boost converter takes that fluctuating battery voltage no matter how low it gets.
And boosts it up to a rock-solid, stable 5 volts.
It's like an electronic fuel pump, ensuring the engine gets steady pressure even when the fuel tank is getting low.
That's a great analogy. It's what separates a quick prototype from a device that actually performs reliably in the field. That circuit alone teaches comprehensive product design thinking.
Which sets us up perfectly for the next shift. If we can build reliable, portable gadgets, we can use that same power and precision for some serious utility.
Now we're getting into the Nano's highest capabilities. We're leveraging its precision analog to digital features and its ability to synthesize voltages.
Let's start with the diode decontinuity tester. This is just a great, simple diagnostic tool.
It is simplicity engineered for utility, and you can see that portable power system again, the LiFePO4 battery, and another plus 5V boost converter, which just highlights how critical that is.
And the Nano's job is pretty straightforward here. It generates a test voltage and then just measures the component's response.
Yep, and the results are shown on an OLED display.
Why an OLED for a field tool like this?
2 reasons. Low power consumption and extremely high contrast. It's readable outside in the sun, and it doesn't drain the battery, which is ideal for a tool an engineer keeps in their pocket. For the measurement itself, the probes connect to an analog input. You need that to accurately measure the voltage drop across a diode.
And the user interaction couldn't be simpler. It's just a single button to toggle between diode mode and continuity mode.
It's the simplest UI possible. You push a button, the Nano changes its internal program, and the same hardware performs 2 totally different functions. It's all about efficient hardware reuse.
Okay, let's talk about the big one. This is where I think the true power of this project-based learning really shines. The curve tracer. This isn't just a gadget. This transforms the Nano into a sophisticated piece of lab equipment.
I agree completely. This is the most technically advanced project in the collection. It uses almost every major capability of the Nano. The goal is to generate a really precise range of test voltages and then measure the component's reaction with equal precision.
So how does the Nano, which is a digital device, generate that smooth analog test voltage sweep It has to be incredibly precise.
This is pure engineering ingenuity. They use 8 of the Nano's digital pins, D5 through D12, to drive what's called an R2R ladder network. This network is basically a highly accurate external digital-to-analog converter, a DAC.
Let's break that down. What does using 8 digital pins for this R2R ladder actually get you?
It gets you resolution. Because they're using 8 pins, they have 8 bits of information. That lets the Nano define 2 to the power of 8, so 256 distinct, tiny, precise voltage steps.
Wow. So it can generate a beautifully smooth, staircase-like voltage ramp for the component it's testing.
Which is exactly what a curve tracer needs to map its behavior.
And that output voltage goes through an amplifier.
Hmm.
But the real intelligence is in the feedback loop, how it measures the results.
Yes, the Nano applies a voltage, and then it instantly samples the component's reaction. Both the voltage levels and the resulting current are fed back into the Nano's high-resolution analog inputs, A6 and A7. This closes the loop.
It generates a signal, measures the response, and then it can plot the characteristic curve.
Precisely.
And there's one small but critical detail I see on the A7 measurement input, a protection diode. Why do you need that if you've been so careful with generating the signal?
That diode is the digital airbag for the Nano.
I like that.
When you're testing a device, especially something like a transistor or capacitor, it can sometimes generate unexpected voltage spikes. Stored charge, sudden changes in impedance, who knows? Those spikes could fry the delicate analog input on the Nano.
So the diode shunts any dangerous overvoltage away from the pin.
It saves your tool. It ensures its longevity and reliability.
So if we just synthesize this for a second.
Yeah.
We started with the Nano just blinking an LED. And we finished with it driving an external DC with 8 digital bits, reading back 2 high-res analog measurements at the same time, and protecting itself with a diode.
And that synthesis is the core lesson of this entire collection. It shows that the limitation isn't really the microcontroller itself. It's the cleverness of the external circuitry you pair it with. You've just transformed a $3 to $5 chip into what could be $500 or $1,000 worth of dedicated lab equipment.
All through ingenious analog and digital design.
That's it.
We've really spanned the entire range here. We went from the immediate gratification of mixing light and rolling dice all the way to designing a fully portable, professional-grade, 3-function tool with proper power management.
And we wrapped it up by showing its capability as a precision engineering instrument. This versatility, it's the driving philosophy behind that project-based learning approach. It's the whole basis for the book, Project-Based Learning the Arduino by Dr. Godre and Naaman Puri. They are proving that hands-on application is the absolute fastest path to deep understanding.
You're not just reading about how a boost converter works. You're actually solving the real-world problem of stabilizing the voltage on your portable Morse tutor.
Exactly. You are moving from abstract theory to functional, diverse, and robust circuits.
And as we conclude this deep dive, I want to leave you with a final thought, building on the complexity of that curve tracer. We saw the Nano use clever external design to perform a really high-end function. So consider this. What everyday device, something you assume must be using a highly specialized, custom-built, expensive chip, could actually be secretly powered by something as simple and low-cost as an Arduino Nano, purely because its surrounding circuitry is so ingeniously designed?
It's a great question to think about. The answer is often far simpler and way more reliant on clever circuit design than most of us would ever imagine.
Thank you so much for sharing your sources with us and allowing us to take this deep dive into the powerful potential of project-based electronics.
Keep that curiosity sharp and remember the power of the microcontroller. It's a universal platform for both, playful creation and serious utility.